Hello, everyone. This is the lecture for section 4.9, Newton's method. So this is, again, one of the applications for a derivative. And this one, like it states here in the notes, it's got a really good crossover into computer science, okay? This is one of the main methods that we use to approximate values that we don't know. So what I mean by that is like the square root of 2, right? The square root of 7, pi, okay? We have an understanding of what those values are, right? But we can't, there's no, like the processes or the equations that will give us sort of like the decimal representation of these values is very, very complicated, okay? Some of these can't be solved by hand, okay? So what we need to do is we needed to sort of create processes so that we can at least have a working version of this number, at least in decimal form, right? And that's what Newton's method does, okay? This field of mathematics, it's its own field in its own right, under the sort of like the umbrella of math. It's called numerical analysis. Basically how we can create processes, or if there are processes that exist that help us numerically analyze certain equations, certain discoveries, you know, all that good stuff, right? So Newton's method is the very, very first one, at least on paper, that was sort of figured out. And as the name states, Sir Isaac Newton is the one that actually coined it. So let me get into it, okay? The first thing I want to define for it, it's not in the book, but I think it has enough sort of, it has enough meat in there to actually define one, okay? To actually give it a definition. And that's the definition of an iterative process, okay? So an iterative process is a process that produces a sequence of values. I'm gonna call these x1, x0 to some x of capital N, okay? So I'm saying that, you know, we have, it's basically a successive number of values, right? Okay, such that as we take the little n to big N of all the xn's, okay, that gets closer to an x star. And what we're gonna do is we're gonna call that our solution, okay? So basically what we're saying is this right here, that as we go that way in the list, right? As we go that way in the list, this is approaching some x star that is our solution, okay? And there's one more thing about an iterative process, is that xn, any value in this list, okay, is based on the result from the previous step of the iteration. So basically, x2, right, depended on x1. x3 depended on x2. That's what I mean, okay? Every single number in this list, okay, is based somehow, right, is reliant somehow on the value before, okay? So that's the definition of an iterative process. Newton's method is an iterative process, the very first one ever, okay? So what I wanna do now is, let's go ahead and start getting into this, okay? One thing I want to recall, because we are going to need it now, is something from section 4.2. Do you guys remember the linearization or the tangent line approximation for an equation at a point x equal a is going to be given by this formula right here, okay? So if you can't recall what that sort of like the theory behind the linearization function, don't worry, the notes are there, go back and look, okay? So now let's go ahead and cover Newton's method, okay? So first of all, like I said, I like pictures. I'm gonna be explaining this as we go, okay? So suppose we have a function f of x. So that's what I'm gonna start with. And I'm making it big just so that I don't lose anything and I have enough space to write on. So what I'm gonna do is I'm gonna draw this equation in this thick blue here. So I'm gonna do And I didn't do that right. Whoa. There we go. Okay. I'm going to draw. There we go. Yeah, let's make it a little more pronounced of a curve. There we go. There we go. So this is my function f of x, okay? This is my function f of x. Okay. So let's say for this function, right, we want to find a root. We want to find this point right here, right? This has got to be some, and I'm going to start using the notation that I have from before, some x star, comma, 0, okay? But we don't know what this thing right here is. We don't know what that value is, right? Okay. This process, Newton's method, is to find that x star, at least a really good approximation to it, okay? So here's how that process works, okay? Let me make this a little smaller now. And actually, I'm going to use a pink. There we go. So the way that this is going to work is like this, okay? I'm going to choose any x0, x of 0 value. I'm going to choose any x value. I'm going to choose this one back here, okay? This is going to be my x0, okay? And I'm going to make it a little smaller so I have enough room here. There we go, okay? So we know, and I think I didn't draw it beneath the function itself. That's not good. There we go. X of 0, okay? We know from section 4.2 that there is a linearization here. There's a tangent line approximation, okay? Let me actually make it a little longer. I need to make it longer. There's a tangent line. I'm drawing on this little thing on a little pad. And it just keeps scooching out at me, okay? So this point right here is x0, comma, f of x0, right? It's the x and the y value. And that line is the tangent line approximation. So I'm going to call this L0 of x, okay? It's given by this formula right here. All right? And what we're going to do now is we're going to find the root of this line. So that root is, I'm going to use a green here. Okay, we're going to try to find that root right there. Okay, so that means we need to solve for when this thing right here is equal to 0. That's this thing. And if you solve out when x is equal to 0, when you solve out for x, you get specifically this right here. Okay, and what we're going to do now is we're going to call that x1. So this point right here is now, and I'm going to make this a little tinier because that looked a little thick there. This point right here is x1. Okay. Okay. From here, we know that it belongs to a point up here, right? This is x1, comma, f of x1. Okay. And at this point, there is a tangent line approximation as well. Okay. I'm going to extend this a little farther that way. This is going to be L1 of x. Okay. And notice how this is working. It's based off of the root of the previous tangent line approximation, right? So now I'm going to do it again. I'm going to find the root of this point, or of this line, of L2 of, or L1 of x, right? So I'm going to be, this is L1 of x, right? The green one. We need to find the root for that one. That means we're doing the exact same process, right? If you solve out for x, you get this right here, right? Notice how this x1 right, was found from the values from before. I'm going to call this new value x2. Okay. Therefore, x2 comma f of x2 has a value there, right? And again, what I'm going to do is there's a tangent line approximation there. It goes through here. I'm going to call this one L3 of x, right? And now I'm going to get a new root for that line, that point right there. That is now x4, or x3, sorry. And I didn't label the one before it, x2. There we go. Okay. I can continue on, okay? Continue and continue and continue. I'm going to stop at x3 at least in terms of the picture. I stopped at x2 in terms of the values and the functions and what we were solving, right? But we can continue this process over and over and over again, okay? And what's going to happen is this. We are going to have, I'm going to go ahead and color code these. We're going to have values of xn, specifically, this is 1, this is 1, this is 1, this is 1. If we continue in that same process, we're just going to keep stacking on x sub n values, right? And they are going to have associated L sub n values, right? L sub n equations, the linear approximations. So here's L0, here's L1, and this was supposed to be L2. Oopsie, L2. Let me get my notation down right. Okay, so on and so forth. Okay, and these roots are based off of the values from the previous values in the sequence. Okay, so if you take a look at the equations themselves for the roots, here's the first one, right? Here's the second one, right? And specifically, take a look at this. So it's going to be x1 there, and then x1 here. You guys see that? So x1 is based solely off of values from x0, x sub 0, right? x2 is based off of solely values of x1. So it keeps going. x3 is going to depend on values from x2. x4 is going to depend on the values from x3, so on and so forth. And in particular, in this iterative process, we get a sort of standard sort of formula that shows up, right? You guys can see how similar they look. To summarize that formula, it's this one right here, okay? So x sub n, right, is equal to xn minus 1, the previous value, minus the function divided by the derivative at that x minus 1 value. Okay. As you can see in the picture, okay, these values xn, let me get rid of some of the color coding here. As you can see, some of the values of the xn's, right, they start approaching something. Those green values that are above, right, they start approaching the value that we want. We want this answer right here. We want this answer right here, right? We want that x star. We want the root of the function, right? We want the root of the function, okay? So what we can say now, right, is the limit as little n approaches big N of the xn, of that sequence of values, or green values and the x-axis, right? They start to equal the x star, okay? And therefore, right, we can start to say that f of x star, right, it should be pretty darn for some n sufficiently large, okay? What do I mean by n sufficiently large? Okay,
That's what the next sort of line right there says. And so in practice, what happens when we do this iterative process, we basically say, oh, we're going to take this process, we're going to do this iterative process. We're going to keep doing these steps until we get to a solution. Okay. The most common way of determining whether we're close enough, right, is when our tolerance, basically, is when the gap between two x values, right, between the xn and xn minus 1, an x value and one thing before it, we say we're done if the distance between those two values is less than some tolerance, less than some error. Okay. Once we reach that tolerance, we stop the process, and we can just say x of n is a pretty good approximation to the root of whatever we need. Okay. So you don't have to keep going with this forever. If you do, you'll get a really, really better approximation of whatever you have done, right? But in practice, we usually stop after a little. Okay. So how does this work? Right.
So what I'm going to do is I'm going to do an example for you. Okay. So you can see what's going on. Okay. So this example is going to be, we're going to consider this function, f of x is equal to x squared plus 3x minus 1. Okay. If you run this through the quadratic equation, okay, we know that this thing has roots. It has roots here and here, the plus and the minus of that thing. So if you want to go ahead, crank out a quadratic equation for this, that's some pretty good pre-calculus review. Go ahead, okay? But that's the roots. What I'm going to do is I'm going to provide an approximation to this value, okay? And what we're going to do, that x sub 0 value, the x naught value, we're going to start it at 1, okay? And that's going to be our initial guess. And we're going to let our error be 0.003. So we're going to stop once the difference in the two values, right, is less than 0.003. Okay. Okay, so here we go. I'm going to go ahead and start computing this a little bit. Okay. So x sub naught, x sub 0 is going to be 1. All right. So if we do 1, and I don't know why this is, I know why. There we go. Okay. So if I let x not be 1, right? My x sub 0 is going to be, it's going to be L sub 0. Come on, go. L sub 0 of x is going to be 5x minus 2, right? The root of which, right? I'm going to calculate the plus 1 now, okay? So the root of which is going to be x sub 1 is equal to f of x sub 0, right? Minus f x of 0 over f prime x of 0, okay? I forgot to do this. F prime of x is 2x plus 3. We're going to need that, right? Let me rewrite this something smaller. X1 is going to be x of 0 minus f of x of 0 all over f prime x of 0. So this is going to be 1 minus f of 0. So we know at 0, it's 1. It's going to be 1 squared plus 3. That's 4 minus 1 is going to be 3. Divided by the derivative at x0. So it's going to be 2 plus 3 is 5. Okay. So and that means this is going to be equal to 0.4. Okay. So 1 minus, oops, the other way around. 0.4 minus 1, right? that is 0.6 about, right? It's not within our error, so we're gonna keep going, okay? But now, this right here is our x1, 0.4, okay? A second. Okay. And now I'm going to now find the linearization. So this is going to be an L1 of x, right? I'm going to find the linearization to this function at this point. This looks pretty confusing right now. Whoa. Why'd you do that for? There we go. If you do this, the L of x is going to be 3.8 x minus 1.16, okay? The root for this, right, is going to be, so now I'm gonna do x2, I'm doing the next one, right? It's gonna be x1 minus f of x1 over f prime of x1. It should be equal to, x1 is 0.4 minus, oh boy, semi-unprepared, calc value, 0.4, 0.36 divided by, 2 times 0.4 plus 3, 3.8. If you do this, you should get 0.30526, right? So now, 0.30526, and it's going to be negative there, right? Minus 0.4, that is equal to negative 0.0947. So it's still not within our our error. So we're going to keep going. We're going to do one more step. We have x2 now. So x2 is going to be 0.30526, right? So give me a second. I'm actually doing this on a calculator, which I'm about to show you guys how to use right now. And I hope you guys use it in doing your own quick checks and your own homeworks. It's much better to do it this way than doing it by hand, okay? So the next one down, right? L1, or L2 in this case of x, is going to be 3.61052x minus 1.09318, okay? If you do the math outright, okay? So then now we can compute x3, right? Is going to be x2, right? Minus f of x2 divided by f prime of x2, which is equal to x2, so 0.3, and I'm going to write it, do this, 0.30526 minus f, I'm going to do this just f of 0.305. Now it's becoming messy. You do equal 0.30526 minus f of 0.30526 over f prime of 0.30526. And this should be equal to 0.30278. Okay. So now this is going to be, so if we want to now take the difference between them, right, 0.30278 minus the one that came before it, so minus 0.30526, right? Let's go ahead and compute that really quick. 0.30278 minus 0.30526. This right here is now 0.00248 negative, right? And now, look at this. We didn't even need the third one. This right here is now less than our error. Our error was supposed to be 0.003. This is 0.00248. We are done. Okay. Boom. Right. So now let me go ahead and sort of show you guys something here. And I'm going to highlight x0. X0, x of 0 is 1. So the sequence of numbers that we went through was we started out at 1. Okay. The next one down was 0.4. The next one after that was 0.30526. And the last one is 0.30278. Okay. And what I want you guys to do now is I want you guys to go ahead and find a value for the positive one. That's the one that we were trying to find the root for. We were trying to find an approximate value for this thing right here. And it turns out it is pretty darn close to 0.30278. Okay. Pretty neat stuff, huh? Okay, so what I want to do now is you guys see how much effort we have to put in to computing stuff like, and I just pulled these numbers out. For you guys, it would seem sort of like out of thin air, like how did I compute them? I did have a calculator to compute it. So what I did in Desmos is I created a Newton's method calculator for you, just so you can see, so for a specific X value, okay, it'll give you the tangent line approximation and you can find the root of the next one. And there's a table there so that you can keep a track of your X values as you move along. Keep a track of those X values as you keep writing, as you keep hitting them, okay? So what I want to do now is I want to show you guys how to use that calculator, okay? I am going to do a split screen here so you guys can see both the screens. You guys can see what's going on here, okay? So here's the calculator. I would highly suggest, this is one of the very few times I would have to suggest this, though it does work on a phone, try to find yourself a big screen of some sort, okay? Either a tablet screen or a laptop screen or a full-fledged computer screen. I think that's what's gonna work best, okay? So I'm gonna rerun this process, this example, okay? And I'm gonna start it at 1, okay? I'm gonna zoom out so you guys can see what's happening. I'm gonna thicken up the lines a little bit. There we go. So that everybody can see the contrast shows up there. All right, so I'm gonna start this example again. I'm gonna show you guys what I've been doing on the Newton's method calculator, okay? So here we go. I'm gonna start at 1. So notice that's where my A is. A is equal to 1, okay? It gave me the tangent line approximation over here, right? There it is, right? And the root of it is going to be 0.4. So I'm going to go ahead and tally that here. So first of all, I'm going to write 1 in for the very first point. Okay, notice how it gave me the point. The next one is going to be 0.4. Okay, I'm now going to change my A to 0.4. It's giving me the tangent line approximation there. So I need to zoom in close. My next point is my 0.30526. I'm going to tally that. 0.30526. Okay, I now get to change this to that value, 0.30526. Okay, it gives me now, this new blue line is giving me the tangent line approximation to 0.030526. I get to zoom in one more time, and look how far I'm zooming in now, 0.30278. 278. Okay, and notice those are our 4 iterations that we did right here, right? That was our sequence of values, our green values, right? Okay. So for your homeworks and for your lecture questions and for the quick checks, please don't try to do this by hand. Try to do it with the calculator that's been given. You can do it by hand if you want to, if you're so courageous enough to do it. There are lots of spots where you're going to make an arithmetic error or an algebraic error. And those are just, make you so angry when you do them, right? So try to skip them as best as you can. Try to use the calculator wherever possible, okay? Get through the process. For these problems, so long as you give me the sequence of values, so long as you give me this table that's right here from the Newton's method calculator, I'll be perfectly fine with that submission, okay? Okay, so what I want everybody to do now, this is the quick check part, okay? I have a couple functions here, okay? And I want you guys to find the roots of them, okay? And I want you guys to find the roots with the Newton's method calculator, okay? Don't make it too difficult on yourselves, please. Do the calculator. In essence, what you guys are doing here for these 4 quick checks is you are finding approximate values for certain square roots. So for group 1, you guys are finding an approximate value for the square root of 2. For group 4, you guys are finding an approximate value for the square root of 7. Okay. Okay, so go ahead, submit at least just the table, at least that table from the Newton's method calculator. Okay, and I'll be okay with that. Okay. All right, so there are a couple problems with this process. Okay, sometimes the speed matters, right? The speed, it might take a little while. Okay, so when we did the example the very first time, right? When we did this example the very first time, we did it in 4 iterations. It took us 4 steps, right? Or actually 3 steps. It took us 3 steps to get close enough, right? Okay. That's one problem. And the other problem is maybe it starts looking for something else. And this is quite, it happened. It happened. So these 2 examples are going to show us exactly that, okay? No matter what, though, it'll do what it's intended to do. It'll find a root, okay? If everything is done correctly, okay? So let me go ahead and do the first, okay? So it's the same equation. We are still trying to approximate the same value. We're trying to approximate the positive one, so -3 plus the square root of 13. But this time, we are going to start at a simple -1. So I'm going to get rid of this right here. Okay, I'm going to run that. So we know we want this root right here. Right? Okay, so we're going to start. My very first value is -1. I'm going to start at -1. Okay.
So I'm going to start here. My A, I'm going to make it negative 1. All right, here we go. So it gives me the tangent line approximation at x equals negative 1 for this equation. Okay. The root of it is 2. So I'm going to put down 2 now. So now we're going to go ahead and go. I'm going to change it to 2. I'm going to get the tangent line approximation at x equals 2. That will see way the heck up there. Gave me the tangent line approximation. And the root of that tangent line approximation is 0.7143. 0.7143. I'm going to change this now. 0.7143. Okay. You hit it again. Tangent line approximation, that's the blue line. The root of which is 0.341. 0.341. 341. Again, tangent line approximation. Try it again. 0.30317. 0.30317. I have to change this again. 0.30317. This again is the tangent line approximation. That's 0.30317. And I'm going to zoom in again. And now I have my 0.30278 that we got from our base from above. Okay. So what I want to do here now is I'm going to take a picture of this right here. I'm going to paste it here. Okay. So notice what happened here, right?
The only difference between the original statement of the problem and this statement of the problem, right, is that I started out at -1 rather than +1, okay? And what happened to our list, look at this, right? We needed this many before. Now we have an additional 2 steps. Okay, so then what this did was it added 2 additional steps, basically, right? Iterations. Let me write that correct. So in this version, it added 2 additional steps, right? Everything else was the same. The only difference is this, that we started at a different point. Okay. This happens. Okay. So in your lecture questions, there is going to be an actual problem that I'm going to make you guys do. It's going to have a couple more iterations than usual. Okay. And when you look at the X values, you're going to be thinking, what the heck is this guy making me do? And all of a sudden it'll start to settle down. It happens. It's sort of like you got to trust the process. All right. Keep going with it. Okay. If you're confused on how this works out, I'm going to be in my office hours if you need it. Okay. You can project your Desmos page for me, and we can figure stuff out. Okay. So in this version, it added 2 iterations, right? So now let's go ahead and do the very last one here. Okay. And then after this, thankfully, yay, it's lecture questions. Okay. Same equation. We're still approximating the same thing, right? But now we're going to start at x0 equal -2. So I'm going to reset my my graph here. Okay. And I'm going to make this -2. Okay. I'm going to zoom out so we can see the whole graph. you guys can see what's going on here. Okay, here we go. Here's our graph, right? Hopefully you guys see what's about to happen. Okay, so what I'm gonna do is I'm gonna go through the process again, right? And we're gonna see what's gonna happen. So my very first point was -2, all right? The calculator is giving me the tangent line approximation, and that root for it is gonna be -5. Okay, so I get to change this to -5. Again, a tangent line approximation way up there, the root of which is going to be -3.714, -3.714. Right, so I get to change this to -3.714. Again, a tangent line approximation. The root of which is -3. What was it again? 3.341, -3.341. Right? So I get to change this now, 341. Again, the blue line is my tangent line approximation. I scroll in there, -3.303, right? -3.303. I'm going to change this to -3.303. Okay, I'm going to scroll in there. And I get -3.303 again. So at this point, we're basically going to say, you know, this is a pretty good root for -3.303, right? Or for f of x, right? It's going to be -3.303. Hopefully you guys can pick out the problem though. Let me scroll out. There we go. Okay, and what I'm going to do is I'm going to go ahead and take a picture of this table. Okay, I'm going to paste it in over here, and I'm going to take a picture of the graph itself as well to post it in as well. Paste over here. So now I'm going to go ahead and shove this over here into our notes. I'm going to put this, make it a little smaller so it fits in right there. And I'm going to grab this and throw it on over here too. And throw it in down here, right there. Yeah, let's cut off that 0. There we go. Boom, so that everybody sees what I'm doing. Let's zoom into this. Let's take a look at what the problem is here. I want to make that graph a little bigger. So hopefully people have been able to pick out the problem that's occurred here, right? So we have a sequence of values and they approached the value. They approached -3.303. You guys see that? Okay. But the problem is we were trying to look for the positive one. So we were trying to look for this root way over here. But what did our process do? It found the one way over here. You guys see that? And the only difference, again, right? The only difference is because we started out somewhere else. We started out at x equal -2, okay? So the process still worked out. It found us a root, just not the one we were aiming for. Does that make sense? So if we wanted to find the square root, or sorry, an approximate value for -3 minus the square root of 13 divided by 2, then -3.303 is a very good approximation too. Okay, but we weren't looking for that one. We were looking for the positive one. Okay, all because we started out in the wrong spot. Well, let me not say wrong spot, in a different spot. Okay. Okay, this is, like I said, the very first version of an iterative process that's ever been found, okay? It's really, really long, drawn out, complicated. A lot of the work that needs to be done sort of behind the scenes is nearly always now done by computers. This whole section, if you ever use Newton's method within your own subject, whether it be engineering or physics or chemistry or psychology, if you ever need to use this method, this is probably one of the very few times ever you will see it done by hand. And that's that I didn't entirely do it by hand. I did it using the aid of a calculator. I used decimals, okay? So don't be ashamed. Don't, please, please, please use the calculator whenever you can, okay? Use the calculator whenever you can, okay? Hopefully hopefully the video is at least sufficiently instructional to get you guys using the calculator comfortably. If it still looks a little daunting, if it still looks a little scary to go ahead and use it, stop by my office hours. Please, please, please stop by my office hours. Come to my drop-in Zoom hours. I'm in there usually 3 o'clock to 6 o'clock every day, Monday through Thursday, okay? Or just send me a discussion post, send me an email, smoke signal, something, okay? Besides that, study hard, and I'll see you guys around.